Okay, we'll get started. Is everyone having a good week so far? All right, okay. I want to answer a couple of questions people had on the first assignment. And you may also ask me, any questions you have at this time on the first assignment. And I'll also, answer some of the other questions or concepts before we go to new material. So the first question people had was, what do I mean by 4 significant digits? Okay. So if you look at CD, it's a very, very small number, right? It's so it'll be 0 point, let's say 0, 1, 0, 2. This is the fourth significant digit, okay? So this is what I mean by the fourth significant digit. Why is it important? Because delta CD of 0.0001 is called one drag count. Okay. Okay, yes, sir. Yeah, I'll do that. Yeah, thank you. One drag count, okay? So engineers pay very particular attention to the last digit, the fourth digit in the CD. Because let's say aerofoil 1 has got a CL of 0.5, CD of 0.0102. The airfoil number 2 has got a CL of same CL, but say that the CD is 0.0104. Okay? If you round it off to 3 digits, you won't get to know which is better, right? On the other hand, if you look at it, even though this looks a very small difference, fourth digit, the L over D is going to be 2% off, okay? CL over CD of airfoil 2 is roughly 1.02 times CL over CD of airfoil number 1. Now, aircraft range, how far they can stay, how far they can travel, depends on V infinity times lifted drag ratio. So the lifted drag ratio determines how far you can travel. Endurance, how long can it stay up in the air, depends on just the L over D. So if you have a glider or if you have a search and rescue vehicle over an ocean or on a desert looking for survivors, the higher the L over D, the better they can longer they can stay up in the air. Okay. Same way, when you glide angle, remember you're gliding because you don't have any engine. So you are still flying forward, you are going circle, but you are slowly losing altitude. So this velocity is V infinity. The lift is in this direction, drag is in this direction. So what balances the lift and drag? It is the weight is acting this way. Pardon me, the lift would be, the weight of the aircraft would be acting this way. So a component of the weight, is what is providing you the overcoming the drag, okay? So if you look at it, I'm sorry, I kind of, the aircraft is traveling, this way. So the L is perpendicular to this is the lift, this is the drag, This angle is the glide angle, glide angle, GLIDE angle. So that will be the same as this glide angle. So L times, let's call it as some angle equal to chi. L times the cosine of chi will be the weight. D times will be balancing the weight. Actually, let's do it this way. This is the chi. L equal to weight times the cosine of chi. And then the weight will have a forward component. D equal to sine of chi. So D over L equal to tangent of chi, where chi is the glide angle. Let me draw this picture a little bit clearer here, because I made a lot of erasures. So the aircraft is going this way, airplane is this way, weight is this way, lift is this way, drag is along the flight path. So this angle is called chi, glide angle. So weight times cosine of chi is the lift, weight times sine of chi is the drag. So if the drag is very high, then the glide angle will be very high, okay? So you will descend very, very steeply, okay? So a glider that is going round and round and round, if it had a lot of drag, it is going to be descending, losing altitude very rapidly. So unless they hit a thermal somewhere or some other source of propulsion, it will climb up, they are going to land on the earth for sure, okay? So you need to have a very good L over D. That means the D over L must be very small to have a very shallow glide angle. Same thing with the climb angle. You could show that it is proportional to L over D. Okay, the higher the L over D, the more rapidly you can climb and gain altitude. So, for example, fighter aircraft get off the ship deck, they need to go very, very far, very, very fast up. Of course, they try to achieve it with a lot of thrust. But if you can aerodynamically make it a more efficient, very high L over D, your climb angle can be very, very steep. So all of these things mean L over D is very important. So even a 2% L over D is a very, very important. Okay? That's why we never round it off to just 3 significant digits. We write it to 4th significant digit. So 0.0001 is called the drag count. Okay, so when the companies talk to each other, they will say, my new wing has got a 2 drag counts less drag than yours. Okay, they will have a team red, team blue. There'll be a design group leader. They are working on the same objective, but they are looking at different configurations. Okay, so they will look at the drag count, because the lift is determined by the gross weight of the aircraft, payload, fuel you're going to carry, structural weight, and so forth. Of course, the structures, people will be trying to make the structures as light as possible. So this is why I said you have to use the 4th significant digit. So that's very important. The second question people asked was, how do I plot the CP distribution? Do I plot it normally, negative to positive, or positive to negative? The answer is, it's always positive to negative, just the way X-foil plots it. Okay, look at how X-foil plots the CP distribution. So this will be X over C. So if you have an airfoil, you have some point here called the stagnation point. We'll talk about it. You get the highest pressure there, okay? And then the flow kind of goes over the upper surface. Then the flow goes to the lower surface. So right at the stagnation point, you'll have the highest CP value. Okay, that highest CP value will be somewhere here, close to 1.0 or so. Okay, one is a theoretical maximum for incompressible flow. Okay, Then as the flow goes over the upper surface, if you use the upper surface, the pressure will start decreasing, so Cp will even become negative. Okay. Then somewhere over here, the curve kind of turns over. It starts coming this way. On the lower surface, you get a curve like this. I have exaggerated this angle just to show you the difference. In reality, this distance is just a couple of %, so you don't see that bend so much in your pictures. So it's always we plot it from positive to negative, okay? So please use that convention. That's what we use. You already know aerospace engineers are kind of weird, and this is one of the reasons we try to plot everything upside down. Can anybody tell me which is called the favorable pressure gradient? Where is the pressure dropping? A favorable pressure gradient is where? Is it here or is it here? Verbalize it. Okay, yes, sir. Yeah.
Further right.
To the right? Okay. Here the pressure is rising, right? Because this is Cp is, you may remember last time we non-dimensionalized gauge pressure divided by dynamic pressure. So if the pressure is rising, it's called an adverse pressure gradient. Think of a poor molecule moving in the boundary layer. You slow it down by the viscosity, and it also has a higher pressure in the front compared to the behind, so it's pushed back. Okay, that's called an adverse pressure gradient. Okay, so this is the favorable pressure gradient. As we saw in our last lecture, adverse pressure gradient can do transition, flow may become laminar to turbulent. That's one bad thing can happen. Okay, but it could also cause the boundary layer to separate, called a stall. So the boundary layer on the airfoil, boundary layer will look like this. It's a velocity profile like this. This is the outer flow. This is the boundary layer. These molecules that are moving through this boundary layer are being slowed down by two effects. One is the wall is slowing you down, skin friction is slowing you down, but the adverse pressure gradient is slowing you down. So depending on the airfoil design, sometimes along in here, the bottom layer of the airfoil will become a zero pressure gradient, okay, zero velocity gradient. So the particles are standing there, they neither move forward nor backward, okay, they kind of come to a dead stop. That's called a separation point, okay. So this is called a separation point. At the separation point, if you look at the velocity profile will look like this. This is the velocity. This is the distance. So the slope of the velocity, u with respect to y is 0. So du dy will be 0. In undergraduate flow, you would have studied something called the Stokes relations. Are you following back there? Hello? Are you following? Okay? Don't be doing anything else, please. Okay? Let's be paying attention. We are covering important concepts. This is a separation point. The shear stress at the wall, which is viscosity times du dy, will go to 0. So that's an indication of the separation point. Downstream of it, the flow may actually reverse itself, so it's going backwards, so it's a fully reverse flow. So when that happens, we say the aerofoil has stalled and it has got a trailing edge stall. Okay, so this is an indication of a trailing edge stall. That means trailing edge means the back end of the aerofoil, and the adverse pressure gradient can cause the flow to reverse itself. Not always, at a 2 degree, 4 degree, 6 degree, you won't see that at all. But at a 12 degree, 15 degree, you may start seeing it. Why? Because this is getting more and more negative. What goes up must need to come down. And when that happens, you have a very steep pressure gradient, then the flow cuts reverse. Yes, please. Yeah, Felix. Yeah. separation point is the same as where the du dy is 0. That's called a separation point. Is that what your question? No, transition will occur much earlier. The flow may become laminar to turbulent somewhere here. That's a totally different reason. The turbulent flow forms. So that's called a transition point. Separation point is a different point. They are not the one and the same. Yeah, good question. Okay. Now, certain aerofoils, especially some aerofoils, have a very, very peaky, pressure distribution near the leading edge. Especially, sharp nosed aerofoils or a low radius of curvature aerofoils. Some aerofoils will have a very, very rapid, a very small radius of curvature, okay, very rapid variation in the curvature. So when that happens, sometimes they will get the CP value, again it goes from positive to negative, way up here, and they may start very steeply, pressure may start changing near the leading edge, okay. So when that happens, this will usually be a low radius of curvature. Thin, usually a very thin airfoil. Remember gliders, people were making early days of gliders, almost zero thickness, but it did have some thickness to the leading edge, like Wright brothers did. So think of it as a very, very thin fabric with some kind of a blunter nose, if you will. Okay. Now, this pressure gradient, so adverse, it may become separate before transition occurs, coming back to Felix's question. So you may get a laminar flow, then you may get a separated flow inside here, still laminar. So this this bubble-like shape is called a laminar separation bubble. Okay, the flow may separate inside. Then, this because the velocity profile has got an inflection point, it may become turbulent. Okay, so there's a theory by Lord Rayleigh that says a velocity profile that has got one kind of a curvature. Think of it as a convex curvature followed by concave curvature has got an inflection. So when the velocity profile has got an inflection, it's inherently unstable. If you give a small disturbance, it'll become turbulent. Okay? So it may become downstream here, the flow may reattach itself, so attached turbulent flow. Okay? So this may occur on this is on the upper side. Lower side is something like this. So this and this look very similar in behavior, except that this peak is very, very high and is very sharply dropping near the leading edge. Okay, so very steep adverse pressure gradient. Now what happens if you go to higher angle of attack? If you go to, let's say this is equal to alpha equal to 4 degrees, say, this is just an example. The same aerofoil, if you go to alpha equal to 6 degrees, you have a laminar, then it may separate right at the leading edge. Okay? So you have a very steep pressure gradient. Then the steep pressure gradient, not only it separates, but the bubble cannot close. It becomes an open separation. So you get some other behavior like this. So you get a leading edge stall. Okay. Laminar flow has got a less mixing, molecular mixing. Remember I said the coffee analogy. If you had a cup of coffee, sugar at the bottom, hot coffee on the top, it'll take a long time for the sugar to migrate and mix up. Turbulent flow stirs things up very, very well. Okay? So this laminar flow has got all the high velocity up on the top, all the low velocity near the bottom. There's not a lot of mixing taking place. Therefore, when the adverse pressure gradient comes, it'll say, to hell with it, I'm going to separate. It becomes a leading edge stall. Okay? So early glider people, who had a relatively sharp nose airfoils, they were stalling very, very quickly. A lot of accidents were happening. Okay? So Wright brothers tried to blunt the leading edge a little bit, but modern airfoils have a relatively large radius of curvature, rounded nose airfoils. They do better. They tend to have a trailing edge stall. Okay? So airfoil itself, there's a lot of interesting things going on. Transition to turbulence can occur. Trailing edge stall can occur. Laminar separation bubble can occur near the leading edge. Across behind it, it may become attached turbulent flow. Or you may have an open stalled flow right near the leading edge. Leading edge stall is deadly, right? You're flying quietly, suddenly a gust hits you, you stall. So people do not like a leading edge stall. They like a trailing edge stall that progressively grows because you get plenty of warning. Okay? Stall warning will say, hey, you're going to stall, reduce your angle of attack, okay? Or increase your forward speed. You want to achieve the same lift, but you can decrease the lift coefficient by reducing the angle of attack. Okay? So it'll give you that information. So in my lectures here, I have a picture, a video of airfoil stall, very, very short video. So I'm going to kind of okay, I'm going to park just a little bit before that. You saw the fully stalled flow, right? Navier-Stokes is needed. Really, a CFT-like technique is needed. Our code, Xfoil, will do its best. It tried to come up with some empirical way of predicting the stall. But in the attached region, we have a lot of faith in our Xfoil. Okay, the drag polar, CL versus alpha, CD versus CL. We can believe it, but when it has an extensive separation, eventually you have to go to CFT-like technique. Fortunately, designers are not designing aircraft to be operating in the stall regime unless it's a highly maneuvering fighter aircraft or some other reason. Okay? They are usually trying to cruise at a low angles of attack, so attached flow is more important to them. Okay? So just this one assignment and material we have learned so far has a lot of interesting concepts in it. So please become familiar with it. So the second question was, how do I draw the CP? Always plot from plus to minus. Be able to identify the favorable pressure gradient, adverse pressure gradient. And adverse pressure gradient can cause two things to happen. One is transition to turbulence and also separation. If the separation occurs at the trailing edge region and progresses forward, that's a trailing edge stall, which is preferred. But for certain sharp nose airfoils or a small leading edge curvature airfoils, that separation may occur right near the leading edge, in which case it may produce a small bubble. Downstream of the bubble, everything starts going from left to right again, but the flow is turbulent. Okay? So turbulent flow reattaches. At the higher angles of attack, it may abruptly separate from the leading edge, and it may become a leading edge stall. Okay? So these are some of the concepts we should become familiar with. Any questions so far? Yes, please.
In leading edge stall, we still have laminar flow after the leading edge stall, or just
most likely it'll be turbulent. Okay, it'll be a highly unsteady, turbulent flow. Okay, the flow is so reverse. It's at that inflection point, and also more region for the eddies to form and draw and so forth. So like that video we saw, at high angles of attack in the flow, it's highly unsteady and turbulent. Okay, yeah.
Can we say that in thin airfoil, the transition point is similar to, or the more closest to the separation point?
Since they are two different phenomena, it's kind of hard to categorically say that. Transition point, we have to look at where does the flow separate laminarly or at least has an inflection. So we have to focus on inflection. So it's possible to have an inflection without separating. Okay, so inflection without separating. So downstream of it may become turbulent. But same physical cause, adverse pressure gradient can cause both of them. But we cannot say, they will be close to each other or anything like that. Yeah, yeah. Thanks. Yeah. All right. The homework is due this weekend, right? Isn't that right? So, please don't be sending me a lot of questions on Sunday, Saturday. I will not be able to answer that many questions. We have over, I think, last count of it, a lot of students in the class. If you have questions, please try to ask it by Friday, please. Okay. After that, it'll be hard for me to answer it. Okay. All right. Abbott and Deinhoff, we talked about different aerofoils are cataloged. A lot of information is given there. We talked about it. So all of these things we have covered. So now I'm going to review some very basic material on streamlines and vorticity. I'm going to completely skip Navier-Stokes equations. How many of you here have taken 6009? Can I just see a show of hands? Okay. Viscous flow. How many of you have taken a viscous flow class in an undergraduate level? Okay. How many of you have heard of Navier-Stokes equations? Okay. That's what I want to know, because it's been probably will be covered in a mechanical engineering course or a civil engineering course, of course aerodynamics. So the Navier-Stokes, we are not going to spend too much time on this, only because we don't have time to go over it that much detail. But Navier and Stokes, their work came towards the end of the 19th century. Navier started working around 1890 something. Stokes in 1900 something. So that's when the Navier-Stokes equations happened. For almost 60, 70 years, they could only solve some analytical problems. Flow through a pipe, flow between a flat plate, things like that. Then in the 1914, 1915, it was simplified and became a boundary layer equations, Prandtl's boundary layer theory. How many of you have heard of a boundary layer theory? Can I just see a show of hands? Okay. Alrighty. So that's based on, some of these concepts stem from the boundary layer theory type of a material. I have all the undergraduate material, posted different places in my website. But that's a background. But long before Navier and Stokes, there were two guys, who were making contributions, because in the 17th century is Newton, right? 17th something is Newton, 18th century is Newton. Okay? 19th century, there was a Swiss scientist called Euler, then another one called Bernoulli. Euler, Bernoulli started looking at the flow field. They did not have the wherewithal to develop Navier-Stokes and then solve them, but they were looking at flows in a much more fundamental manner. Let me look at a group of particles moving through space. Let me see what happens to its pressure, velocity. They didn't even worry about temperature because it's a very, very low speed flow. Okay. So there are two types of ways they could have handled it. One of them is called the Lagrangian approach. In a Lagrangian approach, you start with a group of particles. particles. Then you kind of follow their transition, follow their motion and change in properties. They will go to the same clump of particles, will go somewhere else here. So they may start at some x, y, z, and t. They may end up at x plus delta x, y plus delta y, z plus delta z, t plus delta t. So time has changed, position has changed, the property has changed. The property may be velocity, could be pressure, it could also be temperature, something else. Okay. So let's say that let F be a property of interest. Example, we already have talked about properties of the fluid, pressure, or U, or V, or W component of velocity, you name it. So we have some function here, f of x, y, z, t. By the time it goes here, it has changed x plus delta x, y plus delta y, z plus delta z, t plus delta t. Things have changed. Okay, this is very common today. When you look at the weather person, weatherman or weather lady, they will say this storm front is going to be moving from Alabama to Georgia. This is when we are predicting it to happen. So we're going to be watching its water content, temperature to see whether it's going to snow or things like that. Okay. By the way, watch for me email from me on Saturday or Sunday. We will know the weather situation for Monday more better by the time. And if it looks like campus a warning, then I will send you an email to do an online class on Monday. Okay? I'll send you there's a Zoom link in Media Gallery. I'll resend it to you so you can join me online. Okay? But if the weather is not that bad, we will physically meet here in the class on Monday. Okay? Just watch for it. So that being a side commercial, so when the properties are changing, you are changing it this way. Airplanes do that. When you go on a long distance flight, or even from Atlanta to California, your monitor will show you your change in the altitude, change in the ambient pressure maybe, change in the velocity, change in the different properties of the aircraft as a function of time. Okay, so that's called a Lagrangian approach. People use that for a space shuttle, keeping track of satellites and everything. That's one way of doing it. Other way is Eulerian approach. Eulerian approach is comes from that Swiss scientist Euler. You have a fixed region. Think of it as a wind tunnel. As the flow comes in and the flow goes out, you're just watching what's going on in that region, in that intercontrol volume. So in a wind tunnel, that picture we saw, the particles are moving. You're not following the particles. You're just focusing on what's happening in that region. So here it's called an Eulerian approach. Okay? So Navier-Stokes equations are primarily an Eulerian-based approach. You have a fixed control volume. Flow comes in, flow goes out, like this room. People come in, people go out. So rate of change of mass, you can track it. Rate of change of momentum. If somebody comes running in, cannot be my class because nobody is that excited to come in, but maybe for the next class, then the momentum has gone up. Okay, then you have a rate of change of momentum. Okay, so those type of things you could do. It's a fixed control volume. So both approaches have been followed, and they are kind of related to each other. Here, because x, y, and z are held fixed, so any change in the derivative is just going to be partial derivative. X, y, z are held fixed, right? So that property you are looking at a change in the velocity or a pressure at a point with maybe a pressure gauge or a velocity probe. You're tracking changes in time, but the probe does not move from point to point to point, so it's a partial derivative. Okay. Now, we can link this and this together by using a Taylor series expansion of this function f. Okay. So we could say that the final state of the function, it's the pressure or velocity equal to, we can Taylor expand it about x, y, z, and t. Okay? So we are going to use a Taylor series. We will truncate it after the first order terms, because the second order terms will eventually go to 0 when everything goes to 0. So the leading term would be f at x comma y comma z comma t, which is the starting value. Then you'll get a delta x times df dx at the starting value, starting location, okay, at the starting point, x comma y comma z location. Then you'll have a delta y times df dy. Same thing, delta z times df dz. And let's not forget delta t times df dt. So we get a longish expression like this. Okay. Now, if you try to take a derivative of final state minus initial state, so the final state is f of x plus delta x, y plus delta y, z plus delta z, t plus delta t, minus initial state, which is x, y, z, and t, divided by delta t. After and before, take the difference over a period of time. We are taking a time derivative, but in a Lagrangian coordinate system. Okay. So all I have to do is bring this leading term to the right side and divide everything by delta t. Okay. So I'm going to get the leading term is going to be the df dt, which I found here in the Eulerian coordinate system, holding x, y, z fixed. But I will also pick up contribution from this and this and this. So I will get plus delta x times delta t times df dx, delta y over delta t times df dy, plus delta z over delta t times df dz. And just to make the math professor happy, we can say higher order terms, Taylor series terms. Okay, delta x squared, delta y squared, and so forth, delta x times delta y, and so forth. Okay. Since I had to take my calc three times, I don't remember what these terms exactly look like, but I do know the first leading terms. Okay, this is what we do. Now, as delta t goes to 0, this becomes a derivative. I'm going to kind of erase this a little bit to make some room. Goes to 0. This left-hand term we cannot use a partial derivative, we cannot use ordinary derivative clearly. So we use a new symbol, because we cannot say d by dt, we cannot say partial derivative of t, because everything is changing. So we are going to call this material derivative, that means the material particles are moving from particle point to point, or substantial derivative. Both terms are used interchangeably in books. Okay. Also, delta x by delta t, remember the particle moved a distance delta x over a period of delta t. So as the limit delta t goes to 0, it will be simply the velocity u. Okay, that's the distance it has traveled in the x direction. Delta y over delta t would be v. Delta z over delta t would be w. So we can replace this by u, v, and w. Okay. And then the left-hand side, we can replace it by material derivative. So what we will get is Eulerian coordinate system, Lagrangian coordinate system derivative, which is the material derivative, would be df dt equal to partial derivative plus u times df dx, p times df dy plus w times df dz. So if you look at the Navier-Stokes equations that I am not going to derive, if you open it up, you'll see the rate of change of momentum will be made of this term, du dt, plus u times du dx, dv times du dy, w times du dz. So what they are doing is, they are doing in a Eulerian coordinate system, but what really happened in a Lagrangian frame of reference, how things have changed. Okay. So in general, you could also write it as an operator, d by dt equal to d by dt, which is an operator, plus u times d by dx plus v times d by dy plus w times d by dz. This is just an operator notation. If you write your velocity as a ui plus vj plus wk, this is the velocity vector we saw in the x direction, y direction, z direction. And if you define a del operator, vector derivative operator, as I times d by dx in the x direction associated with the I vector, j times derivative operator in the y direction, plus k times derivative operator in the z direction, then you can write this in a very compact form, d by dt equal to d by dt plus v dot del. Okay. So in a Lagrangian coordinate system, people will be seeing how things are changing over a period of time as the particle is moving from point A to point B. Eulerian people will only worry about this. So the difference between a Lagrangian derivative and Eulerian derivative is captured by this effect. Okay, that's what's going on. All right? Now, why do you have to write this way? Why don't we leave it this way? The answer is now you can apply it in other coordinate systems like a cylindrical coordinate system, polar coordinate system, spherical coordinate system, you name it, as long as you know the del in that coordinate system, velocity vector in that coordinate system. Okay, so you could have a more general interpretation of it. So after every time some people derive some equations, they will write it in a vector form like this. So this is sometimes called the del operator. Okay. So the bottom line is Navier and Stokes came about, I would say, almost 100 years later, but Euler, Bernoulli were doing it long before that, but they were talking about the streamlines moving through space, how things are changing. That's how they were looking at their world. Okay, so that's what they were doing. So now with that introduction, am I writing it okay? Are you all able to see back there okay? All right. Okay. All right. Now let's go to the review of streamline and vorticity. This is something we cover in undergraduate material. By the way, a lot of the undergraduate material is embedded in here. So whenever I say review, it's something we would have taught. But since we have a lot of people here who are not had the pleasure of having me a couple of times teaching aerodynamics, so I have to teach it one more time here. Okay, so we are going to go in here. Where did I download it? I'm going to go kind of quickly over it. How many of you have heard of a streamline, vorticity? Can I just see a show of hands? Okay. We have about a half an hour, so I'm going to go over it kind of quickly here. But I do have some undergraduate videos where I go through the same thing, so you can review it if you wish. Okay. So this is just a review. So we are going to talk about what are these things. So streamline, you could think of it as a path taken by particles in space, the line that I had drawn earlier. So the particles start at some point in space, then they end up somewhere else. So everywhere on that line, the velocity is tangent to that line. Okay, that's the definition of a streamline. So if you take a small, in 2 dimensions, for example, if this is a velocity vector, you'll have a x direction, which is u, y direction, which is v. So we'll have a vector ui plus vj that will be tangent to this particular line, which is a vector, ending point, starting point, delta s. Okay, so that's called a streamline. Equation of a streamline is just a curve in space. Everywhere on it, the velocity vector is tangent to it. So if you take 2 points on that curve, x, y, z, x plus delta x, y plus delta z, y, z plus delta z, this line vector would be just a change in the x, change in the y, change in the z in the 3 direction. Velocity has also got its 3 components. If they are tangent to each other, their cross product will be 0, right? I cross I is 0, j cross j is 0 because the included angle is 0. Okay. So if you write a v cross delta s equal to 0, you can write the v vector as one row, delta s as another row, do a determinant, simplify it, then when you get this way, you'll get this is the equation of a streamline. Okay. So in our undergraduate classes, we will give a lot of UVW mathematical formulation, ask you all to integrate it, and then come up with the equation of a streamline. I have thrown a couple of worked out examples just so that you get a feel for how these things are used to compute the equation of a streamline. Okay. Have you all seen my announcement about the second quiz? Not the second quiz, the first quiz. Okay, it's going to be on the 26th at 8 o'clock at night from your comfort of your home without any of your classmates sitting next to you giving you help, okay, on your own. You'll have an hour and a half to do the exam plus 10 minutes to scan it and upload it, okay? You can do it by hand, you can do it on your tablet, piece of paper. You won't have time to be typing it, with the LaTeX and stuff like that. Don't even do that, okay? Just do it quickly, then upload it. European students, we have 3 or 4 students in GT Europe. They'll be given a different time window, possibly a slightly different exam because of the time difference, okay? But anyway, I'm going to post a study sheet where I will list all the concepts that you need to know. Okay, so right now absorb it, but I can't cover all of it in my exam, so I'll have a study sheet saying please focus on the following topics. You'll be getting it. Since the exam is on the 26th, which is a Thursday, I most likely will post it on the 12th, which is another Thursday, 2 weeks earlier, February, after my Wednesday class is over. Okay, so I will kind of list it. All right, good. So another group of particles are called the path lines, which are the physical path traveled by a particle over a period of time. Okay, they look very similar, right? Streamline and path line look very similar. But the difference is, if you have multiple particles released at different times, they may look in this picture as though they are crisscrossing each other. Okay, crisscrossing each other. For example, in a football game, one player may go straight down this way, a wide receiver, just go down the sidelines. Next play, the same wide receiver may go curving around. So if you take a elapsed time window over a period of time, you'll see all these paths crossing. There was John Madden was a big TV announcer. He used to be a Oakland coach. He would have a little pen and draw showing all the pathways people are going and so forth. So path lines will seem to crisscross each other because they are really different particles, or at least different place or different instance in time they started. They seem to be crossing each other. Okay? But streamlines cannot cross each other because a velocity vector can be pointing only in one direction, right? So no way at a single point you could have two velocity vectors point two different ways unless it's a stagnation point. If you have a zero velocity, I could be pointing forward, I could be pointing this way, point this way. Nobody cares. Okay? So at the stagnation point, streamlines will split. In the aerofoil example I showed you, the streamlines can come this way, one can go this way, one can go this way because the velocity here is completely zero. Other than that, if you look at those videos we saw, the streamlines will never cross each other, whereas the pathways seem to cross each other. Okay? So how do I define the path line, or what is the equation I use? I just integrate the UVW as a function of time, integrate it, and get the velocity, a position. This is like an inertial system, inertial guidance system on a car or on a spacecraft or even an aircraft. Sometimes you'll keep track of where you are in space in XYZ coordinate system. Okay. So another example is when you go down in here on a freeway, if you take a very, very fast photograph, a high-speed camera, you'll get this picture. Everybody will seem to be staying in their lane, although that's not true, right? Because the cars are going in their lane, so the car motion is parallel to the path of the lane. Okay. On the other hand, if you had an elapsed time periods, let's say even 1 second, this would look like this one. Okay, it seems like the cars are actually crossing each other, but they're not colliding because it's taken over a different period of time. Okay, so this is a pathway or a path line. This is a streamline. And in the steady flow, when nothing changes, they will be one and the same because let's think of all the wide receivers are doing the same routine. Every play after play after play. If you're a Falcon fan, you know what I'm talking about, right? You know exactly they were doing the same thing. Everybody knows what's coming, including the opposition coach. Okay, so then you are never going to cross each other. It's always going to be the same. So in a steady flow, when things are not changing in time, the streamlines and the path lines will be one and the same. In our course, we are mostly interested in steady flows. Therefore, we are not going to be worried about unsteady flows. But Professor Marilyn Smith teaches an outstanding course on unsteady flow where things do change with time. Okay, so we are going to primarily be focusing on steady flows. So streamlines and path lines are one and the same. So we're going to just keep the same meaning. Then let's look at the angular velocity of the fluid. fluid particles can spin and rotate in space, just like a solid particle can spin and rotate in space. Like if I spin this, it'll spin and in 3 directions. So angular velocity is going to have a component in the x direction, in the y direction, in the z direction. So it's got to have 3 components. So vorticity is 2 times the angular velocity. It's a vector because the angular velocity is a vector. We'll explain why did the 2 came from. Because when they were developing vorticity, they had a 1/2 coming up everywhere. It was a pain to carry 1/2 everywhere you go. So you multiply by 2, get rid of it. That's where the number 2 came from. So very quickly, how did it get developed? How did they define it? They knew if you had a large collection of particles, we are talking about vortices, right? This is like the weather person talks about the weather fronts, storms, tornadoes, and so forth. We are talking about a large group of particles, big collection of particles. But in fluid mechanics, you are taking a one point in the space, let's say in an Eulerian frame of reference, or in a Lagrangian frame of reference, the particle is going this way. We want to know how does it rotate. If so, what is the angular velocity? We want to multiply by 2. That's the vorticity. Okay, so that's what we want to find. And now, if you just had a solid, things are a little bit easy because you can just draw a line on a solid, and if the solid rotates, this edge, and that pink line will rotate the same way, same amount. Like, if I had drawn a line here, if I rotated, everything by rotate by the same line. So you could just draw one line and find a rate of change of angle position. That'll be the angular velocity in this direction. Okay. So if you think of this as a vector pointing, if I rotate this way, doesn't matter I take a vertical line or a horizontal line or a line through it. As you know, we have an indoor flying lab. We have helicopters flying around all the time. They put stripes, reflective stripes on the helicopters. Then they make the room dark. They do strobe light, take a picture of it. So the rate at which these lights, strobe strips are turning gives you an indication of the angular velocity. So you could see how quickly can I rotate my, this vehicle, how much thrust does it take, and all kind of a good stuff they could do that. Okay, all right. On the other hand, in the fluid mechanics, we are not talking about solid-like material. We are talking about material that can deform. Think of it like a jello. It can change. So they had to do something a little bit different for fluid element. So what they said was, okay, let me at least take 2 sides, this side and this side. As it goes from point A to point B, as it rotates, this edge can rotate one angular velocity. This may rotate at different angular velocity because it can deform. So I'm going to take the average of the AC phase, AC line, how does it rotate? And AB line, how does it rotate? I'm going to take an average of it. That's where that 1/2 came from. To get rid of that 1/2 is why they had to multiply everything by 2. Okay. So in this 2-dimensional phase, as it goes from here to here, it has deformed like this. It has gone to some other position. Now, I'm going to show you how do we find the angular velocity of this phase, angular velocity of this phase, and I'm going to take an average. I'm only looking at the component of angular velocity perpendicular to you. Okay? So if this is x, this is y. When x rotates towards y, right-hand screw rule is going to come towards you. Okay, that's the z-axis. So we are going to look at the component of vorticity in the z direction. Are you all able to follow that? Okay? Yeah. Now, what happens is, if you look at just the AC, A has moved to a new position, A prime. B has reached a new position, B prime. They may have stretched, by the way, it's possible to elongate, or they may have compressed, that's also possible. But we are not worried about the bulk changes, in that direction. We are only interested in how much it is rotating. So all we have to see is how much vertical distance the B traveled relative to A. Because they are traveling in the vertical direction, this is at VA, this is at VB. If VB is higher than VA, then the B prime is going to be above A prime. Okay? So the difference is VB minus VA times the time over which it traveled. So that's the vertical distance. Now if you carefully bring that particular line and bring it here, then you'll get a triangle with the included angle of the triangle will produce the angular rotation. Okay? So originally this distance was delta x. The B had moved vertically up faster than A by this amount. So VB minus VA times delta t. So the angle is delta theta. So you could think of the angle as tan inverse of opposite side by adjacent side. So tangent of delta theta is delta theta itself for small angles of attack. That will be VB minus VA by delta t by delta x. So delta theta by delta t, rotation, angular velocity of this face AB is VB minus VA by delta x. That's in the limit as delta x goes to 0 is the d capital V dx. Okay, that's the derivative. So we could do this for the horizontal face, and we could do the same thing for the vertical face. In a vertical face, let's say, has moved. So point C has moved horizontally faster, let's say, compared to A. Then we are going to have UC minus UA delta t. Then the derivative of that face is going to be how U is changing relative to Y. Okay, du dy. But this is rotating clockwise. The other one is rotating counterclockwise. How do I pick the sign? Remember right-hand screw rule? When x rotates towards the y, it's coming towards u, z is coming towards u. Counterclockwise is positive. So we take du dy as a positive number. This dv dx as a positive number. Du dy as a negative number. So the angular velocity is going to be 1/2 of dv dx minus du dy. This is just for this one component. If you do this for all the components, then your angular velocity is going to be 1/2 of, you can write a similar expressions for the ij. You could show that it's this del vector crossed with this velocity vector. So you pick up this 1/2. We don't want to carry this 1/2 everywhere. That's why we take the 2 to the left-hand side. 2 times omega is what we call vorticity. Okay, so vorticity is a vector. So that's how the vorticity comes about. And in our aerodynamics, we have a lot of flows where you have a lot of vorticity. Boundary layer is a clear example. The boundary layer may be like say a millimeter thick, but the velocity may go from 0 meter per second to 100 meter per second over a millimeter thick boundary layer. Okay, so we are talking about a very large du dy in the vertical direction. So there's a regions of flow where we have a lot of vorticity, but outside the boundary layer, vorticity is almost negligible. Okay, so when you have a negligible vorticity, we call it an irrotational flow. Okay? So in our class, we are primarily going to be dealing with the inviscid irrotational flow. Hope whoever taught you 6009 earlier class talked to you about the viscous flow sufficiently so that you can at least pass the PhD quals and move on with your life. Okay, or if you're not taking it as a flow quals, you don't need to worry about it even. But there's always the viscous region present underneath it that's causing transition, that's causing stall, that's causing turbulent flow. We do need to be aware of its presence. We cannot forget it. Okay, so we're going to be talking about outside the boundary layer. But there are other regions, other flows where we also see vorticity. For example, jet boundaries. In the core of the jet, velocity will be more or less uniform. But outside the jet, because the core is moving faster than the top, This is like a moving sidewalk. If you go rapidly, put your foot in there, you will rotate this way, right? Your feet will move forward, your head is moving slower. So you'll have a counterclockwise vorticity. Same way here, the top is moving faster, the bottom is slower, so you'll have a vorticity. So whenever you have a jet boundaries or a velocity layer boundaries, sometimes you get to vorticity. Okay? So this is an example of rotational flow that where we cannot neglect the vorticity. And boundary layers, as we mentioned earlier, over a short thickness of a millimeter or so, the velocity goes from 0 to of the order of v infinity, 100 meters per second over a 1 millimeter, 2 millimeter thick. So very large amount of vorticity. Again, laminar, turbulent, the transition is where things change. And so boundary layer, we have to worry about vorticity. But outside the boundary layer, we can assume the flow to be inviscid. By the way, if you have a very, very bluff body, you have such a large region of vorticity, you can't solve it with X-foil, which assumes I have a large inviscid flow. Thin boundary layer, they interact with each other. That's what X-foil is doing. Remember, it does an iteration. Some of you had an iteration convergence issue. Did anybody have iteration convergence issue by any chance? You did at CL of 0.4? Okay, already. I was going to tell you after I have taken off 15 points or so from your grade, but let me show you what you do with it. Okay. Are you all able to see my screen okay here? Can you see better now? Okay. Can you sleep better now in the back there? Okay, already. Okay. So this is what we are going to do. So let's say NaCa 0012. Then basically, it has done 160 points on the airfoil. Basically, it's a discrete representation of an airfoil, right? So sometimes near the leading edge region, with such a coarse representation, then you may have sharp, ragged edges on the airfoil, okay? So think of a rock. If you define it only with few points, it'll look like sharp edges, right? So the reason at 4 degrees it does not converge, is because we have relatively few points. So X-foil provides two ways of improving the panel method. So one of them is called let me put a question mark. Question mark will give you all the commands that you have available. There's one called pin. You could panels based on the curvature, regions of very rapid changes. You'll pack the points there. It'll smooth very shallow regions of curvature. You'll have fewer points. That's one way of redefining it. Or you could also use another command called pcope. You have to kind of play with it or read the manual on it. I have done neither, but let's see what happens. Pcope. And I'm going to put some number, 320 or something like that. I want to do the pcope. Now I have double the points, 331 points on the airfoil. So what I recommend is you increase the number of points on the airfoil so that a ragged, jagged airfoil becomes a smooth airfoil in the eyes of X-foil. Now if you do a OPER and then go to VASC, and then if you put it 306, and by the way, go ahead and increase the iteration number to large number just in case it doesn't converge. Then now specify your CL of 0.4. It's converged. Okay, so if you look in here, in just 9 iterations, it has converged. Okay, So if you have a problem converging, of course the airfoil may be stalling or there may be some physical reason why it's not converging. This is not a cure-all, but we know NACA 0012 at 4 degrees should not be separating, should not be anything weird going on. So the most likely reason is because we don't have a number of points sufficiently refined. So you could use commands like pane to cluster it near the leading edge, trailing edge. You could also try pcope and see what happens. Okay. Any other problems you have had in the X-file? We only have 5 minutes, so I'm going to just ask questions, then we will stop. Yes, please.
Just a small question. So it wasn't happening with NACA 0012. It was happening with NACA 64A012.
Okay.
So I didn't do pcope or pane, but
see if it helps.
Yeah, I changed the iterations to 300. It was not converging at 250 even. So
yeah, sometimes it'll take a large number of iterations. What happens is the boundary layer is growing, and it displaces the flow. The streamlines want to move away from the body. There's one way of acknowledging the presence of the boundary layer is to put a vertical velocity. So in some viscous inviscid coupling, they put the vertical velocity. It keeps changing. It takes a while to converge, especially when you have a large region of separation. Other way people do is physically add that displacement thickness, come up with a new aerofoil, and then analyze it. I think X-file uses the velocity at the edge of the boundary layer to push the flow away from the body. But depending on the severity of the problem, more iterations will be needed for this viscous inviscid interaction to converge. Yes, please.
If you were to instead add more panes, I think you can change the number of panes on there instead of the number of nodes. Would that have a similar effect?
Yeah, the pcope, when I did it, I tried to put it 320.
Yeah.
Maybe 320 is not needed. I could have just typed a pcope, then it'll add more points.
Okay.
Yeah. 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 So, pane clusters in the important regions, and then on the other hand, it coarsens the other places. pcope, I think it actually does the other thing. Yeah. Yeah. Thank you. Alrighty. So let's stop here. We're almost at 9:15. So watch for an email from me about Monday class. It'll be either here or online, depending on the weather. Okay? So be Lagrangian power 1 and follow those tracks as they come from north towards Atlanta. Thank you.